Very good. So what I'm going to talk about in this mini course is a joint work with Patricia Gonçalves and Rodrigo Marinho, which is defending his PhD on Friday, actually, and Octavio Nes, which was my former PhD student, and now he's in Purdue. So, and well, I think everybody knows what CLT means, so that's essentially a theorem. But maybe you don't know what Ness means. So Ness states from non-equilibrium stationary states. Okay, so what is a non-equilibrium stationary state? Is not something which is actually well defined from a mathematical point of view, not even from a physical point of view. It's more or less it's more than something more like an idea, but it's these non-equilibrium stationary states are present everywhere in nature and are and we don't really have well understanding of them. And so I'm going to present you some examples, try to start to explain why they could be they're interesting and why they could be interesting also from a mathematical point of view. So the challenge that we face is how to describe non-equilibrium stationary states in a mathematically rigorous way. Okay, so this is an example. So hurricanes, for example, are a non-equilibrium stationary state. So how does hurricane more or less work? So what a hurricane does is that it transfers energy or heat, let's say, from the sea to the atmosphere. Okay, so the stratosphere is cold, the sea is hot, and these two objects they serve as reservoirs for this hurricane. So in this hurricane you have this central column that you can see in the picture here. This is this point in the middle, the eye of the hurricane, that serves as a connection between these two heat reservoirs. And the hurricane, basically what they do is that they transfer this heat from the sea to the atmosphere, and of course it's a spectacular type of heat transfer that is happening there. And it turns out that it is this thing here. It is an example of a non-equilibrium stationary state, because you see you have these two heat reservoirs, and in the middle, actually, the hurricane is in a stationary situation. Okay, and you see here that the stationarity is not what we understand. Usually, we confuse a stationarity with equilibrium. That there are two different physical concepts, no? Because you say that something is stationary if it doesn't change in time. But when you say it doesn't change in time, it means that the statistical properties, for example, don't change in time. It's like when you look at a stationary stochastic differential equation, for example, the Ornstein-Uhlenbeck process or something like that, is stationary in time. So the law is Gaussian, and with fixed mean and variance for any time, but it doesn't mean that it's constant in time. It's not the same thing. No, it has some non-trivial evolution in time. So the same thing here is dramatically true from a hurricane, where the guy is actually stationary in that sense, but of course it's not. The evolution is not constant in time. You have dramatic effects if you encounter one of these guys in nature, right? And this type of systems are ubiquitous in nature because non-stationary, non-equilibrium stationary states are very efficient in various ways. Okay, so one possible way to think about the what does it mean is in terms of heat transfer. So they transfer energy from place to place in a very efficient way. And there are other things that, so for example, if you look at the Markov chain, so I think everybody heard about Markov chain Monte Carlo, which is a way to simulate some target measure, some target probability measure. And then you use a Markov chain, and the question there is how long you have to run your Markov chain until you get to the target measure. And it turns out that non-reversible Markov chains, so Markov chains on which there is some drift somehow, have a tendency to be much more efficient than reversible Markov chains in order to simulate a target measure. And that's a more mathematical way to say that these non-equilibrium stationary states are very efficient. Okay, because in that case, what we're saying is that if the target measure, instead of being an equilibrium stationary state, which is what you say when the Markov chain is reversible, is non-reversible, then it's a non-equilibrium stationary state. Then the simulation runs faster. Okay, so this is another funny example of what is a non-equilibrium stationary state. Is that the sun is also a non-equilibrium stationary state. And something which is remarkable about the sun is that it has been stable for thousands of millions of years, no? And so you see that in the sun, there is also this transfer of energy between the nucleus, now the center of the sun, and where is the place where the actual nuclear reactions happen, to the surface of the sun. And then, of course, in the surface of the sun, you have this release of energy to the Earth and so on. But but the system itself, it's again in a non-stationary, a non-equilibrium stationary state. It's stationary in time. Okay, so what we receive from the sun is basically constant in time, but this stationary state is very dynamic. No, there are a lot of things going on there. Okay, so when you ask to physicists what does it mean a non-stationary state, it's a physical system which is stationary in time, but on which you have the presence of currents. Okay, non-trivial currents. Okay, so there are things flowing from one place to the other, and that fact characterizes the non-stationary, non-equilibrium stationary state. Okay, so and these currents could be in a sense external, in the sense that, for example, in the case of a hurricane, you have heat flowing from the sea to the stratosphere. But they could be also internal, because the hurricane is actually whirling around, and those currents are internal to the system. So they don't actually transport something from some outside reservoir to another outside reservoir. Okay, but anyway, there are currents. Okay, so and these currents are what characterize this stationary, non-equilibrium stationary states. Okay, so but let's go to a mathematical example to try to see what how a stationary a non-equilibrium stationary state will look in a mathematical system. So of course, since we are probabilists, we try to model it with a probabilistic object, and the natural probabilistic object is the Markov chain. Okay, so what is a non-equilibrium stationary state from the point of view of Markov chains? Is just the invariant measure of a Markov chain which is not reversible. Okay, so this is I'm very mathematically sound definition of what is a non-equilibrium stationary state. You can check actually that this implies currents, because any Markov chain can be decomposed in cycles. So this is a theorem. If you want to express it in a concrete way, if you look at an stochastic matrix, so the transition matrix of a Markov chain, you can always decompose it as a product of cycle matrices. And in the case of reversible Markov chain, these cycles have length too, so you just go and go back. And if the Markov chain does not have a reversible, if it has a non-reversible invariant measure, in this decomposition, you have to make cycles of length larger than 2. And then and then you can define the current around that cycle, and you can check that this is non-trivial in the sense that statistically the expectation of this current is non-zero. Okay, so but this is slightly different from the physical definition, because in a physical model there is some sort of homogenization going on. Okay, so you start with a microscopic model, and what you observe are macroscopic quantities like temperature, pressure, density, momentum, etc. And these quantities are macroscopic, so they are averages of the microscopic quantities. And so macroscopically there could be some currents, but macroscopically maybe these currents average out. Okay, so it's not exactly the same thing to say that a non-stationary, a non-equilibrium stationary state is just the invariant measure of a non-reversible Markov chain, to say that to compare it with the physical definition. Okay, but anyway, since we're mathematicians, probably we feel more comfortable with the mathematically sound definition. So that's the point of view that we are going to adopt here, is that a non-equilibrium stationary state, a NES, is just the invariant measure of a non-reversible Markov chain. Okay? So let's go to our first example. So of course we have been stranded at home for more than a year by now, and nowadays everybody knows about these letters, no? Cs, CIR, Cs, Sears, and etc. models. So those are examples of what people call compartment models, and they appear naturally in the modeling of epidemics. And these letters are, so let me explain about the Sears model. Okay, so these letters SIR, they have a meaning. So S means susceptible, I means infected, and R means recovered. And so the idea is that they will have a population of n individuals, and each one of these individuals can be on one of these states. Okay, susceptible, infected, or recovered. Those are the things that people call compartments. And then we have to define some transition rules. So how people get infected, how people get recovered, and how people get maybe susceptible again. Okay, so one way to do that is with the Markov chain, a very simple Markov chain. So the simplest dynamics one can imagine is given by these rates that I wrote here. So this is going to be a continuous time Markov chain. So usually when you look at epidemic models, it's the natural setting is continuous time, not discrete time, because there are these exponential growths that happen, and which means that in different scales, the resolution, if you try to model with a discrete time Markov chain, this discrete time Markov chain will need to have different resolutions at different times, because time scales change depending on the situation, on the phase of the situation of the model. So the dynamics is like this. So a guy gets susceptible if it enters in contact with an infected guy. Okay, and that we are going to say that it's going to happen at rate A plus I. So A, lambda, and mu are the parameters of the model. A is bigger or equal than 0, and lambda and mu are bigger than 0. If mu is equal to 0, we are in presence of the SIR model. Okay, so and A is what I call the immigration rate. Okay, I'm going to explain a little bit about it later. So this is these are the rates. So you go from 0 to 1 with rate A plus I, where I is the number of infected individuals in your current configuration. Okay, and then an infected guy gets recovered at rate lambda. And then a recovered guy loses their immunity with rate mu, okay, and becomes susceptible again. So this defines a Markov chain on the space omega n, which is just a space of possible configurations. So I'm calling the lambda n the set of individuals, and omega n the possible configurations of these individuals, susceptible, infected, recovered. And in this way, you define a Markov chain sigma t. And the first thing is that you have to observe is that if A is equal to 0, then everybody 0 is an absorbing state of this Markov chain. Okay, so if everybody is susceptible, nothing happens. Just if A is equal to 0. Okay, so and then from the point of view of invariant measures, there's nothing much. There's not much to say. It's actually a very interesting system anyway, because you have this metastability phenomenon. That is that if you actually run the dynamics, it goes to stabilize at some point, which gives a positive density to each one of the 3 states. And then because of large deviation situation, at some point there is a very big fluctuation, and you go to this absorbing state. Okay, so first you go to I equals 0, and then people get recovered. Yes, should be exactly. That's a very good point. Let me just correct it. Thank you very much, Roman. So let me see. I have to check the right color. This is the right color. So let's go to 0 with rate. Okay, so that's so this is the SIRS model, and when A is strictly positive, then this chain is irreducible, and therefore it has a unique invariant measure, and this unique invariant measure has full support. And then you can check that this invariant measure actually puts most of the weight around this this point that I was mentioning. So there is a related ODE that has a unique stable fixed point, and the actual invariant measure puts a mass on around that. Okay, so I'm not going to enter into the details. I just wanted to tell you that, give you this example, because the invariant measure of this model is a very simple example of a non-equilibrium stationary state. Okay, because it's a non-reversible Markov chain, and And therefore, we cannot just compute in an explicit way, for example, the invariant measure. Although it's a very simple interacting particle system, we cannot compute this invariant measure in an explicit way. So this is actually this model is actually it's part of the PhD thesis project of one of my students, and the idea is basically exactly that, to characterize and then to describe in a concrete way how these stationary states behave, and it's from the point of view of epidemics. So the other day, so people always ask this question. The other day, one person was asking me, you see, lockdown and preventive measure amount to nothing, because in Australia everything is closed, and now they have an outbreak. Where how is possible that if everything was closed and there were no more cases, then you have an outbreak again? And the answer is very simple, because you see this A here is very, very small, and the disintegration rate, but once you gain a little bit of momentum on this model, you converge back to the stationary state, and the conversion is very quick, although they can be very small. So that was our first example. Another example. Okay, so this is just a quick proof that this guy is non-reversible. It's very easy to check that this dynamics is non-reversible, because actually you see that a cycle 0, 1, 2 has positive rate, but the opposite cycle has rate 0. And you can check. This is fun, because this is a very simple observation. Is that although you cannot compute explicitly the invariant measure of a non-reversible Markov chain in most of the cases, you can easily check that the chain is non-reversible. The only thing that you have to find is a cycle that has different probability in one direction than in the other. So if the product of the rates of this cycle here is different to the product of the rates of this other cycle here, then the Markov chain cannot be reversible. And so in that way you can check. In this case, it's very easy, because you see that one of the cycles has positive rate, and the other cycle has rate 0. Okay, so another example of this thing is what is called the simple symmetric exclusion process in contact with reservoirs. So this is actually a very popular example of a system with a non-equilibrium stationary state. Okay, in fact, this example here was used to develop something called macroscopic fluctuation theory, which is one of the first, let's say, mathematically sound attempts to describe non-equilibrium stationary states, at least for one particular class of systems, which are called driven diffusive systems. So this model here is an example of a driven diffusive system. And how this dynamics work? So we have here a line of length n, and you put particles here. Okay, so if there is no particle, I write 0 at that corresponding point here, x in this line, and I write 1 if there is a particle. And then these particles just perform a simple symmetric random walks. They are time continuous. Okay, so you wait with some rate. So each particle waits, let's say, an exponential time of rate 2. Then it chooses left or right and tries to jump there. If the destination site is empty, the jump is accomplished, as it happens here, right? And if the site is it's already occupied by another particle, the jump is just not accomplished, so you don't do anything. And you see here that, for example, this particle here can jump to the left, but not to the right. But this particle here can jump both to the left and to the right. So that's what people call the bulk dynamics. So that is what happens in the middle, away from the boundaries of this interval. So at the boundaries, something different happens. So what happens is that you imagine that you have two reservoirs, one with density alpha and the other one with density beta. These two numbers are between 0 and 1, alpha and beta. And whenever the first site is empty, like here, you can enter a new particle, and that will happen with rate alpha. And if there is already a particle there, it's going to get out of the system, go to the reservoir with the rate 1 minus alpha. Okay. And at the other end, you have the same thing, but with rates beta and 1 minus beta. So if you do it like this, what happens is that alpha is different from beta. So if the temperatures to the left and to the right, so this alpha and beta, this represents somehow temperature. You can understand it as temperature. So if the temperatures are different, then you will have a net flux of particles from the reservoir with higher temperature to the reservoir with lower temperature. This, what I just defined, is a Markov chain, right? It's just a Markov chain on a nice state space. This omega ends with 0, 1 to the power n. And it's going to be irreducible if, so here also, this is not what I meant, no? What I meant is that the couple alpha beta does not belong to this. So if unless the boundaries are trivial, you will have an irreducible Markov chain. Okay, so if the particle reservoirs are 0, 0, it means that at some point everybody the whole line is going to be empty. And if it's 1, 1, at some point the whole line is going to be full of particles, and then nothing happens. So you will have a disabsorbing state. Otherwise, you have an irreducible Markov chain, and it's going to be reversible only if alpha is equal to beta. In that particular case, you can compute the invariant measure explicitly. So the invariant measure of this in this case is going to be just a product of Bernoulli random variables. Okay, so what does it mean? It means that if alpha is equal to beta, no, then if you put particles independently at random at each site with probability alpha, then you obtain the invariant measure of this Markov chain. So if alpha is different from beta, the invariant measure is non-trivial. Okay, so in this particular situation, it can be actually described in a very complicated way. Okay, so there is something. So if you use a variation of what is called the Bethe ansatz, you can actually compute the k-point correlation functions of this invariant measure. And so there is a systematic way to do that, which is called the matrix method of the RIDA. But the point is that nevertheless, it's very complicated. So it's not so easy to really obtain information out of those explicit formulas. So it's so you can actually describe the measure in a complicated combinatorial way, but that just hints into our previous point that the non-equilibrium stationary states are complicated. And then something that you can check, and that could be interesting, and that is going to be our, in fact, our interest is that the two-point correlations functions you can compute. You can compute how different sites are correlated under this invariant measure, and there are long-range correlations. Okay, so it means that a site near one of the boundaries is actually correlated with a site on the other end, near the other boundary, and this correlation is of the same order as the correlation between two neighboring sites in the middle of the interval. Okay, at least in dimension 1. In dimension 2, they decay, but in higher dimensions, there is a decay, but the decay is very slow. So that we have long-range correlations, and this is actually one of our goals. You can actually describe these stationary states in some way, but the point is that the description is not really easy. It's not very straightforward, and although for this particular example, the simplest symmetric exclusion process, we do have this explicit combinatorial function formula. Of course, is, for example, if the dynamics is non-simple, so if you allow next to nearest neighbor jumps, so jumps of, let's say, size 2, we no longer have the combinatorial formulas to describe the non-equilibrium stationary state of this system. So this is the type of problems that we want to tackle. So from a mathematical point of view, we have this these non-reversible Markov chains which arise naturally in many contexts, and we want to study their invariant measures. And because of the non-reversibility, unless for some miracle we know a priori what the invariant measures are, it's not very it's not possible to obtain explicit formulas for those measures. So as I was saying, this exclusion process is a particular example of what is called a driven diffusive system. Okay, so the actual system I want to present in this course is not the exclusion process, because that's in the case of the exclusion process, the stationary state is not translation invariant. Okay, so it's you have this difference of temperatures, also the reservoirs at different densities, and then that means that when you look at this stationary state, is going to have spatial dependence. So in order to make life simple, because we really want to start to develop some sort of theory, some sort of roadmap to study this type of system, we want something which does not have spatial dependence. That's the case with as well with the series model. So it's a mean field model, but there is another driven diffusion system, which has this translation invariance, but on which the spatial structure is still present. And that's the one that I'm going to present, and it's called the reaction diffusion model. Okay, so particles evolve in the discrete torus ZDN. So what is this? Is just the integer lattice modulo n. Okay, so the integer lattice modulo n is actually a discrete torus. No? So it's periodic in the d dimension, in the d directions, and we will have exclusion dynamics, okay, which is the same as before, as I presented before, but now instead of having an evolution on the interval, we'll have an evolution on the lattice. And in this case, it's a periodic setting, so there are no reservoirs. There are no hidden reservoirs, so the source of a symmetry comes from a different place. So as before, we had the exclusion dynamics. So you go from a set X. So particles go from a set X to a neighboring site Y. So this is what I meant by neighboring. So I'm using this symbol to denote neighbors. So I'm going to use the usual convention on the discrete lattice that the two sites are neighbors if their L1 distance is equal to 1. And you jump among them with rate, instead of being of jumping with rate 1, I'm going to already introduce so you see that in the discrete torus, I already introduce a parameter n. No? So n is a natural number, which is going to be the scale of the model. So as usual with these Markov chains, what we are going to be interested in is in the large scale limits of these Markov chains. Okay, and so n is going to be a parameter that we are going to send to infinity. And since, so if you think about this exclusion dynamics, if you just have one particle on your lattice, it's just a simple random walk. Therefore, the natural time scale and at which you will see things evolve in a non-trivial way is times of order n squared. So therefore, instead of putting rate 1 on the particles, so instead of particles waiting exponential types of rate 1 before hopping between neighbors, we are going to put immediately the proper time scale, so we don't have to add it later. Okay, so the rate is going to be n squared. And there is a reason for that, because the second part of the dynamics is what we call the reaction dynamics. Okay, so let me see. Something we can do. No. So the reaction dynamics is going to mimic somehow what I explained before, the CIS model. So it's actually mimicking another popular model, which is the CIS model. So in the CIS model, you just have susceptible and infected, and you go from susceptible to infected. And now what we imagine is that there is a special component in our dynamics. So if you think about the empty sites as susceptible individuals and occupied site as an infected individual, you see that with rate a plus lambda over 2d times the number of infected neighbors, you become infected. Okay, so that's one interpretation of this dynamics. Another interpretation is just that these are just particles, so particles are created with this rate. Okay, so particles are created with the rate, which is, so there's this A, so it's a, this is what I was calling immigration. So you imagine that your system is not isolated from the outside world. So with some rate, you enter into contacts with outside people that could be or not infected. And that produces this, this number A. Okay, so, and then you are in contact with your neighbors, and your neighbors could infect you with rate lambda. And I'm divided by 2D just to have to not carry a 2D factor in the computations later on. And this, and then an infected guy is becoming susceptible again with rate 1 minus A. Okay, so of course, maybe putting A and 1 minus A is not completely realistic, but the point is that by a time change, you can actually change that, that constant there. It's not very important. And the point is that this is just an example. So it's what we're going to do. It can be done for more general type of reaction dynamics, but these rates are simple enough. So that's a good thing. And they are inspired by the contact process with immigration, or also the CIS model with immigration. So, and notice that this reaction dynamics is not accelerated by N, okay? And you can check that this is the right thing to do, okay? When you look at the large scale limits of these Markov chains, if you want both effects to be on the same foot, the reaction part and the diffusion part of the dynamics, then the time scales have to be introduced in this way. Okay. So I'm going to come back to the actual scaling limits of these models tomorrow, but so today I not really want to enter into that. I want to be a little bit more just to give you a little bit more of the motivations of what we are doing. So the point is that in the way I just define things, we obtain an irreducible Markov chain, okay, in omega n, which is this space, state space here. Notice that this state space here is huge. It's enormous, no? So it has size 2 to the n to the d. So although it's a finite state Markov chain, we already see that we should really see it as a system, no, which says it approximates some continuous object, because from a finite point of view, we are not going to get very far because the size grows too fast. So since it's a reducible Markov chain, it has a unique stationary state that I'm going to call mu SS n. So it's SS is from a stationary state, and it's a non-equilibrium stationary state, because this Markov chain is reversible if and only if lambda is equal to 0. So you can check that if lambda is equal to 0, then the Bernoulli product measure of density A is actually invariant under these dynamics. Okay, so you once more time, you have this very simple way to characterize invariant measure in the reversible case. As soon as the lambda is different from 0, you have something non-reversible. How can you check that? Well, you can just try to find a cycle, no, on this state space of this chain, such that the product of the rates of going in one direction of the cycle is different to the product of the rates of going in the other direction of the cycle. And you can check this. It's not very difficult to do. It's so if you have something like a configuration like particle whole, and you create a particle, then you move the particle, and then you annihilate the particle. That thing has different rates than creating the particle, then moving back, and then destroying the particle. So, so it's a non-reversible chain. Okay, so the objective of the course is going to be to give a characterization in some way of this non-equilibrium stationary state. So I want to describe the large scale properties of this measure mu Sn. Okay, so this is our objective, and it's one particular example of a non-equilibrium stationary state, and it is it falls under the category of driven diffusive systems that I was mentioned before. So that's the usual question. So what we want to do? So we want to describe this measure mu Sn somehow, describe its properties. And what do I mean by describing its properties? Well, maybe we want to find their scaling limits. So notice that when I say the scaling limits of the measure mu Sn, we already have to do something, because of course these measures, they live in different spaces. So we have to put them all together in the same space in some way. And usually what you do in that situation is that you define some observables. So you define something that you think are the reasonable observables of your measures. And those observables now they are going to live in the same space. So those are going to be now random variables defined on the same space. And for those random variables, you want to find the scaling limits. Okay. So then also a natural question, something that people want to know, it's the correlations. Are the correlations of these measures? Okay, so if you have, when lambda is equal to 0, the invariant measure is product. It means that if you have two different sites, the correlation between them is 0. So when lambda is different from 0, you want to know what's going to happen. So, and then what is interesting about these models is that they have this long range correlations phenomenon. So we're going to see that when points are far away, the correlation is actually is not decaying fast. Okay, so usually people say that you have long range correlations when correlations don't decay exponentially fast. Okay, so that's going to be the case here. One can see that, for example, in dimension 1, correlations don't decay at all. And in higher dimensions, correlations decay polynomially fast. This is related, as you may imagine, to the behavior of the green function of the simple random walk on the lattice on dimensions d1, 2, and 3. And you know that the green function does not decay in dimension 1, and then it decays logarithmically fast in dimension 2, and decay polynomially fast in dimensions 3 or higher. And then a natural question, of course, is about universality. What do I mean by universality? Okay, I'm just giving you one model, okay, one example of a driven diffusive system, and then one would like to know whether different models have the same scaling limits. And surprisingly, well, this is going to be true. So if you change the reaction rules, okay, so you make them more complicated, And at least under some conditions, the scaling limits are going to be the same. So they don't really matter about they do not depend on the fine-tuned properties of the dynamics. This is also true for the diffusion part. If you create more complicated diffusion rules, okay, so or maybe if you use independent particles instead of exclusion process or something else, you still going to get the same scaling limits. So those are the usual questions people want to know about this non-equilibrium, in general about interacting particle system, and in particular about this non-equilibrium stationary states. Okay. So let me see. So here it says 11 of 20. So it means that I'm basically at the in the middle of what I prepared for today. So it means that it's probably a good idea to make the break right now. Okay. So it's a little bit less than half of the time, but
thanks, Milton. I don't know, are there already questions?
Okay, yes, something before I forget. So for the moment, it has been a little bit vague. It's just an introduction. So I assume that you don't really have a lot of questions about the mathematics, but today's lecture is not yet prepared, which means that what I'm going to do tomorrow, it depends on your feedback, okay? So please don't refrain yourself to make questions, because that's going to have an important influence on what I'm going to do next. Okay, so and in particular, if I don't have any questions, I won't do anything. No, not really that, but it's not going to be. I mean, it would be nice if if I have some feedback, so I can discuss things which are more interesting to you than to me, probably. Okay, so if you have any questions, please feel free to ask.
So
you can ask whatever you want. Huh?
I have a question.
Yes, Fabio.
Hi.
Hey.
Yes, so without asking for a precise mathematical definition, but how in general do you define a driven diffusive system? I mean, what is a broader class? Okay, diffusive I understand, but driven diffusive, apart from these two examples, what? Yeah.
So let's say so let's put it in this way. So I imagine that the diffusive system in the limit is going to be described by a diffusion equation. Okay, and I also have in mind that when I say that, I implicitly telling you that the diffusion equation is reversible. So it has an so it is in gradient form, no? So you have an invariant, an explicit invariant measure for this diffusion equation. So that's what I call, what I imagine that when I say a diffusive system. It's not only that in the limit is governed by a diffusion, but also that the diffusion has a nice invariant measure. Okay, so you solve you can basically solve the lattice problem almost explicitly, or you have a super good, nice theory that tells you that the solution of the elliptic problem is as nice as you want. Then, so in particular, there are no currents, no, because the diffusion is in gradient form. Then, driven means that you add stuff on your equation in the form of boundary conditions, drift terms, or reaction terms, in such a way that now the equation is no longer reversible. Okay, so you have this parabolic equation. So a general parabolic equation has boundaries, drifts, and source terms, maybe, no, or reaction and reaction terms. And now that you have this setting, no, this parabolic setting, the reversibility is like a miracle, no, to have a stationary solution such that the generator of this parabolic equation is self-adjoint with respect to this stationary state. Is kind of a miracle, and those are the systems that in my head are driven diffusive systems.
But for instance,
And
if
then,
you take,
of course, yes.
Yeah, for instance, if you take the symmetric exclusion and you add some asymmetry, does that like WASEP or ASEP, does this?
Yeah, exactly. That's for me. That's a driven diffusive system.
Okay.
It has to be WASEP because you want in the end to have a parabolic equation still.
Yeah,
but
you
this
want
is
like
a
parabolic plus the. Yeah. Okay, I see. Understand. Okay, thanks.
And for example, actually that was an example that I erased from the notes, but it's a good example. ASEP on a ring, no? So if you have these exclusion particles going evolving on a ring with an asymmetric law, it's not longer 1/2, but you will do PQ, then this Bernoulli product measure is still invariant, but it's no longer an equilibrium measure, right? Because you have current of particles, so it's a non-equilibrium stationary state. And there you can actually formulate this efficiency thing in a very nice way, because the spectral gap of the exclusion process, of the symmetric exclusion process, is of order 1/n², and the spectral gap of the ASEP is actually of order 1/n⁵. So the spectral gap is much bigger for ASEP than from SEP. And which means that from the point of view of if you want, for example, for simulating, in this case, the invariant measure is just product, so it's not very interesting to simulate, but in the point of the mixing properties are much better. And you see that the cost of changing the system from symmetric to asymmetric is basically zero. No? If you want to think about the computational terms, the computational cost of simulating the symmetric exclusion process and the asymmetric exclusion process is the same.
Do you have a good reference for that?
No, this is incredible, but it's actually I've been saying this as if we were a very well-known fact from like 10 years, and it seems to be actually a conjecture. So for TASEP, you can actually compute the eigenvalues. So for the totally asymmetric exclusion process, okay, with this Bethe ansatz, and then you can check that the spectral gap is of that order. But the point is that this should be true for any asymmetric particle system on a ring.
Mm-hmm.
And this is completely open problem.
Leandro also had a comment.
Yeah, so Leandro?
Hey, Milton, sorry. I was just wondering if by any chance, well, so if you follow somehow, like you could try to normalize according to the current, right, as well. And do you still recover what I mean is, suppose that you're in ASEP, sorry, I think my camera's on, yeah. And you follow the middle particle, whatever, instead, and you shift according to this particle. So depending on the measure that you start with, I was just wondering if you counter your flow in certain ways that is not necessarily just taking the average. Do you recover the old result, if you see what I mean?
No,
or
no.
do you still feel the
really,
presence?
Yeah, you still feel the presence of so it's so for example, let me put it in this way. So if you have a symmetric random walk on a ring, The spectral gap is 1 over n squared. If you have an asymmetric random walk on the ring, the spectral gap is still 1 over n squared, because you can do what you just said. You can just follow this particle around the circle, and what you see is a symmetric random walk. Right? But as soon as the asymmetric mechanism is nonlinear in some way, the nonlinearity of it, I mean, creates this additional mixing that makes things fast.
Okay.
So it's very persistent, this mechanism of.
No, fair enough. I was just wondering. Thank you.
Okay. So Milton, how was it? Do you want to make a break now, or?
Yeah, maybe just 5 minutes to get a coffee, and
Okay.
then we come back.
Yeah, so let's do that. So let's resume, I don't know, 2021 or so.
Okay.
Whatever time it takes you to get a coffee.
Very good. Okay, so okay, yeah. So let me explain you now what I sometimes call the dynamical approach. Okay, so we have this non-reversible Markov chain, which is irreducible and therefore has a unique stationary state mu SSN. But it's completely, we don't have any information about it. So how do we actually identify it? How do we obtain information about the stationary state mu? So the idea is to use the dynamical approach. So, well, first we have to decide what do we mean by a scaling limit, under mu SS. So what we have in mind is that we define some random variable xn that for some reason we consider is the right thing to look at. Okay. So this is what I like to call observable, because this is what is how you call it in physics, no? But in probability, we just call them random variables. And what is a random variable? It's just a function from omega n to some Polish space E. Okay. And of course, since omega n has it comes with a measure, no? Our invariant measure mu SSN. That means that xn induces a measure on E, and that measures now are all defined on the same on the same space. So we can talk about weak convergence or convergence in your preference on your favorite sense as n goes to infinity. Okay, this still doesn't tell you anything because we don't really know mu SSN. So we have to do something else, and what we do is that we let the chain tells us about what its stationary state is. Okay, so this random variable xn is actually the limit of something else. Okay, so let me denote by STN the semi-group generated by the chain. Okay. Then you start your chain from your favorite initial condition. Okay, so here, since you only want information about the stationary state, you are allowed to choose as your initial state the most convenient state. Okay, it could be something, it could be anything. Okay, so maybe you are ambitious and you say, okay, I don't want to make any assumption on the initial state. Or maybe you are clever and you say, okay, you know what? I believe that this stationary state looks like the following measure. So I'm going to start my process with that measure from the beginning. And then you let the system evolve. And what you do is that you observe the observable xn along the trajectory of the processes, sigma t. Okay, so notice that I didn't put a t here, no? That's what people usually do. What actually is to put a t there is just the same as saying that the limit is taken under these particular measures, no? Because if you change the measures on your space, you change the distribution of the random variables, and then you change your theorem. So what you do then? So you let the chain evolve up to time t, and you look at your observable at that time, and you see whether this guy has a limit or not. Okay. So it may have a limit, it may not have a limit. Of course, here I'm already thinking that I took the right time scale to get limits, no? Because I was, as I was telling you before, I already defined my reaction diffusion dynamics with these rates n squared and proportional to 1 in the case of the reaction, in order to have a well-defined limit without making any further change on the time scale. Okay, so the first thing that you do is that you try to prove this thing here. Okay, so whatever observable you're using as your description of your stationary state, or the state of the system in general, you prove a limit for it. Okay? This is something you may or may not be able to do. Then, now you have a continuous object, no? This xt, well, maybe, probably continuous, no? Because probably the space E is a continuous space, okay? And then what you do is that now all these random variables xt, they live in the same space again, no? Because they live in the space E, so the question about the limit when t goes to infinity is well posed. And usually, then what you want to do is that you want to see these xt random variables as a process. And this process probably satisfies an equation. And now that you have an equation, you can send t to infinity and see what happens with this equation. And usually this is easier to do that at the beginning because your limiting object is easier to characterize. And that's the idea of this universality thing. You know? Actually, this process is going to be the same for a wide class of Markov chains. And then the step 3 is to change limits. No? So you see, I'm writing this. This is kind of is too optimistic thing, because you see step 1 and is very difficult. Step 2 is probably easier, but still difficult. And step 3 is possibly the most difficult one. It's basically, it looks impossible, no? Because depending on what your random variables x and r, looks very difficult to exchange these limits. Okay, but if you're able to exchange the limits in n and p, what are you going to be able to do is to prove to prove a scaling limit of xn with respect to the stationary state mu s. And that will give you at least a partial, depending on how good is your, how fine is your random variable xn, it's going to give you some partial or some complete description of the stationary state. And so when you want to exchange limits, Okay. Independently of what you're exactly doing, a very good idea is to have a priori bound. Whenever you want to exchange limits, this is basically the way to go. What is an a priori bound? It's a bound, no? So for example, you can think about, so I mentioned this Polish space E, so usually you want this space E to be a Banach space, okay, because then you will have norms, and a priori bounds is going to be something of the form that the L to let me put it in this way: the second moment of the norm of your process is bounded uniformly in T and N. That's a priori bound. Okay. So because a priori bounds, so an a priori bound in principle doesn't tell you anything about the limits. Okay, so it's just one bound. The second moment is bound. So if you want to prove the CLT, for example, for independent random variables, it's very easy to obtain a priori bound, no? Which is the second moment is bound. You may or may not, I don't know if you've done this, but this is something sometimes I do when I teach a course in probability for people with not such a big mathematical background. They don't feel comfortable about the characteristics functions because, you know, complex numbers are super complex and you don't do that. And what do you do then? Well, then you do an elementary proof, which is more complicated, but it's elementary. So people, so the students they feel more comfortable about that. And how do you proceed with this a priori bounds? No? Because if you assume that your random variables, for example, are bounded, and you try to prove the CLT, you have very nice machinery that you can use. No? You can do this Lindbergh procedure, for example. And once you did the Lindbergh procedure, then you want to prove it for only assuming bounded second moment, and you did a priori bound. And this actually works because having a priori bounds are for independent random variables is not very difficult, but in principle they don't tell you anything about the limit. Also, knowing that the second moment of the normalized sum of independent random variables is smaller than 1 is far from proving that the limit of these normalized sums is actually going to be a Gaussian random variable of mean 0 and variance 1. But these a priori bounds are very useful when you need to change limits later on. Okay, so from now on, I'm going to enter into general tools that works for basically general finite state Markov chains. Okay, so I want to present you with various ideas that are actually good for any Markov chain. So this is like the way to go, because as I was telling you, so characterize this equilibrium stationary state is difficult. So if you really don't want to try to use specificities of your model unless it's strictly necessary, unless you are arriving at the point on which you start to really enter into the details of this equilibrium stationary state. So before that, you want to do something more general because you want to be flexible. So now let me just prepare the setup. So I'm going to talk about now general finite state Markov chains. So some of these facts might be well known to you, maybe less known. So the setup is the following. So I'm going to consider a state space omega, which is going to be finite, although everything also holds for countable state spaces, but then there are some ability problems. So if you can just justify that whatever sum is finite, then you still are in good shape. So as you notice, I'm always working in continuous time. So I really prefer continuous time Markov chains, because when you do discrete time Markov chains, you have to take discrete derivatives in time, and that is annoying. It's much better to take continuous, at least to be able to take continuous derivatives in time. Okay, so of course in space you cannot take continuous derivatives in space for finite state spaces, but at least to have it in time is good. Okay, so let me call xt the Markov chain with rate x r x y. Okay, so since we are in finite state, there is no problem in defining continuous time Markov chain. So when your state space is countable, it's always a nightmare to define a continuous time Markov chain, because you have to guarantee that the chain doesn't explode in finite time. For that, you also need a priori bounds, and so you cannot get rid of these a priori bounds in this context. So let me call L the generator. Okay, so when you're in continuous time, the right object is the generator, is no longer the transition matrix. Okay, it's because it's the generator L, which is basically the transition matrix minus the identity in the case of stochastic matrices, the right object to look at. So this is the generator is that guy there. L of f of x is just the rate of change of the function f. This is the infinitesimal rate of change of is the infinitesimal average rate of change of the function f when the chain is at position x. And let me call mu the invariant measure. Okay, so I'm going to assume that the dynamics is irreducible. Since we're in a finite state, you can always look at the minimal, a minimal subset. Okay, so a subset on which the chain is actually reducible. Since we're interested in the stationary states, it's natural to assume that it's irreducible from the beginning. And if it's irreducible, the invariant measure it exists as unique and it has full support. Okay, all points have positive measure. Okay, so I'm going to need to define another object which is extremely useful in these situations. People not always have contact with it, which is so-called Carrel-Champ. Okay, in English, sometimes it's called the second variation of the operator L. But as usual, you know, the French names, they have this their own charm, and so I prefer to call it Carrel-Champ, and to pretend that I know how to speak French with students as well. And so how is it defined? It's a bilinear operator. Okay, so L is a linear operator. So if you look at the formula here, so this is a linear operator in F, right? So L of F plus G is equal to L of F plus L of G. And this guy here is bilinear. Okay, so it's linear in each one of the coordinates in F and G. And it's defined in this way here. Okay, so it's if you take F equals to G, what you get here is the square of the difference. So that's the name comes from that. Okay, so it's really the instead of looking at the average change on the function f, you look at the average square change. And so this is the definition, and you can check this formula above, that this formula here, no? So let me see. That's okay. So you have this formula here, and then so this Carré Duchamp has an expression in terms of L. Okay, so you can check that if L is a second order operator, then you can use the Leibniz formula to compute L of the product of F and G. And these two terms here are the, so you have basically three terms, and these two terms here are the extreme terms of the formula, and then you only get the middle term, which is actually the product of some gradients. Okay, it's not exactly the gradient of F times the gradient of G, because I'm not saying that L is just the Laplacian. If L is the Laplacian, you get exactly the gradient of F times the gradient of G. But if L is a general second order operator, you get the product of some first order operator applied on F and some first order operator applied on G. So this is the Carré-Duchamp, and you will see that it enters in a very natural way when you perform computations with the following object, which is the density of the process. Okay, so let me call Ft the density of the distribution of xt with respect to mu. Okay, so I'm not talking about the initial condition for xt. So let's assume for the moment that xt just starts at the deterministic point x0. It's just a finite state Markov chain, so it's not very important for the moment. It's and then this process has a law at time t, and this law has a density with respect to mu, because remember that mu has full support. Okay, so there's also no problem in defining ft here. It's just a nice, well-defined function, bounded in time, and etc. And this ft satisfies the Fokker-Planck equation. Okay, so if you want to look at the evolution of ft, you take the derivative of ft with respect to time. What you get is L star of ft. Okay, so this is just the Fokker-Planck equation, and L star here is the joint of the operator L with respect to the L2 of mu. Okay, so it's the joint operator in the sense of inner products with respect to mu. And since the invariant measure, since mu is the invariant measure, this operator L star is also a Markovian operator. No? Is actually the generator of the adjoint dynamics of xt. So there is something that people call the entropy method. It's used. It's very used in stochastic analysis when you study diffusions. Also used in PDEs when you look at the evolution equations. And it's they call it the entropy method. So the idea is to somehow to measure the distance to equilibrium. So, well, not equilibrium now, because it's not reversible. The distance to the stationary state mu as a function of t. So how do you measure this distance? So if ft is equal to 1, you are at the stationary state. Okay. So if f of t is different from 1, you are not at the stationary state. Therefore, the distance of f to 1 is a possible measure of the distance to the stationary state, of the law of xt at time, right? So, and how can we measure that? So it's one possibility, and this is possibly the most general way to do it, is to define a strictly convex function phi from 0 infinity to r. So it's strict. It doesn't not need to be necessarily strictly convex, but it's because maybe you want to do L1 norm, and for L1 norm, this function is not strictly convex, but it's nicer if it is strictly convex. And you assume that phi of 1 is equal to 0. Okay. Then by Jensen's inequality, this object here it's equal to 1 if and only if f of t is constant equal to 1. Right?
You mean zero?
Huh?
You mean equal to 0?
0. Yes, 0. Of course. Thank you. So what is going on? Okay, so this W of t is somehow it measures the distance between the law of xt and the invariant measure mu. And since we are looking at a irreducible finite state Markov chain, we know that everything converges to mu exponentially fast, because just this is just finite state. So in particular, we know that W of t goes to 0 exponentially fast. That's not a mystery, but actually what we would like to know, so that's the information we would like to get, is the actual speed of that exponential convergence. Okay, so if you want the bound of the form W of t is less or equal than c times e to the minus lambda t, and then you want this constant c and this exponent lambda to be as so c as small as possible and lambda as big as possible. And so the convergence to 0 is not a mystery. The exponential convergence to 0 is also not a mystery, but you want to find the guy there. Okay, so now let's make some computations. Okay, so for the moment I'm going to assume reversibility of the chain. Okay, just to make this computation easier. And so if you take the derivative of w with respect to t, well, it's just a formula. You can exchange the derivative with the integral because everything is finite. C is strictly convex, so is in particular is differentiable. So you can do this computation. You discover that is the integral of phi prime f of t times L star of f of t. Now you pass the L star to the other side. Remember that L star is the dual of L with respect to the inner product with respect to mu. So you get that you can pass the L star to the other function. So you get this formula here. So it's the integral of ft times L phi prime of ft. So in particular, this is good because you actually don't really need to compute the adjoint of the operator L. Compute the adjoint could be annoying. So especially if the measure mu is not explicit. So it's good news that we can actually get rid of it just by duality. So if we assume reversibility, okay, then L is equal to L star. And then remember this formula for the Carré-Duchamp that was there. So let me, this formula here. So you see that you have that FLG plus GLF, this guy here, is equal to what? Is equal to L of the product minus the Carré-Duchamp. Okay? So you can go down and replace that into this formula. So you have these two guys are equal. So in particular, they're equal to 1/2 of the sum. And then this 1/2 of the sum, you can replace it by this. So you get L of the product, but the measure mu is invariant. So the integral of L of whatever you want is 0. So that term is 0, and only you only get the Carré-Duchamp. So you get this identity here. So you see, so WT is what people call the entropy. And this term here, gamma, is what people usually call the Fisher information. So you see that the derivative of the entropy is, so the rate of decay of the entropy is given by the Fisher information. This is what usually people say about this identity. Notice that this is an identity. It holds for any finite state Markov chain. Well, it has to be reversible. Okay, this is something we assume. So it's true for any reversible finite state Markov chain. Now, there are two important cases. So although this is true for any entropy, what people really do is to consider two functions or variations of these two functions, because those two functions are the ones which behave nicer. Okay, so the first important case is phi of u equals to u minus 1 squared. So what we are looking at is the L2 distance to equilibrium, if you want. Right? So it's the L2 norm. Well, it's actually the square of the L2 norm of the difference between Ft and F infinity. So 1 is actually equal to F infinity, no? Right? So if you take T to infinity, Ft converges to 1 because the law of your chain converges to invariant measure. So you are looking at that, and this so this is a very so this is what people really study. No, they doing this, we arrive to what is called the Poincaré constant. Okay, so what is the Poincaré constant? So you define lambda as the infimum of that number there. And so it's the infimum of the integral of the Carré-Duchamp. So this is what people call the Dirichlet function, the integral of the Carré-Duchamp with respect to the invariant measure. That's what is called the Dirichlet form in this context. So lambda is the infimum of the Dirichlet form of a density f divided by the L2, the square of the L2 norm of the difference of f with 1. Okay. So you take this infimum. Of course, you have to take it with a little bit of care, because of course, if f is equal to 1, the denominator and the numerator are both 0, and it's actually undetermined. But you can just do a little bit of calculus of variations to see that this infimum is actually well defined. Okay. So so once you know the Poincaré constant, or at least a bound on the Poincaré constant, you can get a bound on the distance to the stationary state. Okay, so because you see that you get that W prime of t is less or equal than minus lambda W of t, and that is you can integrate out this inequality to get an exponential decay for W of t. So here there is something already that people use a lot, which is we start with the Fokker-Planck equation. Okay, so Ft equal to L star of F, ddt of Ft equal L star of Ft. And then we obtain some information, okay, about, for example, this Wt here. So, and as soon as we get something out of the dynamics, we just forget about it. Okay, so you see that here we say, okay, instead of bound, trying to, instead of trying to bound this object, so of course, notice that when phi is equal to u minus 1 squared, phi prime is equal to 2 times 1 u minus 1, so the 2 cancel with the 1/2, and then you get ft minus 1. But you can see that in the, so the Carré-Duchamp is bilinear, so the Carré-Duchamp of 1 is 0 always, so you get effectively gamma of ft. So you have gamma of ft on the right hand side. But now I'm using a bound that holds for any function density f to get a bound on wt. That looks a little bit silly if you think about it, because I'm not using at all the fact that ft is not any function. It's actually the density of the law of my process. Okay, so it's you see it's a little bit silly because, of course, the Poincare constant maybe is small because I'm considering densities that I will never see on my process. Okay, so here there's always a trade-off. Okay, so for example, when if you look at the literature about mixing times, the mixing time of a Markov chain is defined starting the Markov chain from the least favorable possible case. Okay, so you want to know how time it gets. You need to get to the invariant to the stationary measure, to invariant measure, starting from the worst possible case. If you start from the worst possible case, it's very much reasonable that along the trajectory, what you will see, at least for some time, are very bad densities ft. Okay, so they are not nice. So doing this bound here, you know, taking, for example, using the Poincare constant, is not that bad. And then you can also check that when you are close to the invariant measure, ft can, so you can use spectral theorem, and you can write ft in terms of the eigenfunctions, no, the eigenbasis of the operator L, and you will see that the dominant term is actually the guy associated to the eigenvalue lambda, because if the Poincare constant is lambda, it means that the operator L has an eigenvalue with real part equals to lambda. Therefore, although it seems like a long shot, from the point of view of mixing time, okay, which is what some of the things that people study a lot, is not that bad, because there are, if you think about it, so when you look at the trajectory of your process up to the stationary measure, there are two regions which are very important of the dynamics on which you cannot do better. First, the starting region, because you are actually starting from the worst case scenario. So you in the worst case scenario, you're really having densities which are bad behaved somehow. And at the end part of the dynamics, when you are closer to the stationary state, L2 theory starts to work well, and you can use spectral analysis to see that you cannot do better than the Poincare constant. Yeah, so although it seems to be a long shot, it's not. So there is always this trade-off. In our case, okay, so in the problem I described about the behavior of the non-equilibrium stationary state, things are a little bit different, because we're actually allowed to choose as an initial state for this dynamical approach a well-behaved state. So it might be that because of our knowledge of the dynamics, we can do better than the Poincaré constant. And actually, if you really want to go all the way to prove nice results, you need to use all these ideas. Okay, so just to tell you that although it seems silly to use the Poincaré constant to bound L to norm, you cannot do much better. Okay, so another important choice for your entropy is actual entropy. No, well, this is relative entropy. Okay, so relative entropy is also an entropy function, and so it what happens when you take phi of u equals to u log u. So if you do that, what you are computing actually is the relative entropy of the law of the process at time t with respect to the invariant measure v. And people in this case, so they define two different constants. Okay, so K0, which is called the modified log Sobolev constants, is the infimum of that. Okay, so then if you do that again, so you see what is going to appear in the right hand side of the entropy equation is gamma of f log f. So it's natural to take the infimum of that divided by f log f, and then you get this exactly the same bound as before, no? So you get that the w of t decays exponentially fast with the exponent k0. And there is another constant which is more popular because what happens is actually that diffusions, okay, so which means continuous Markov processes, the modified log Sobolev constant and the log Sobolev constant are the same. And the log Sobolev constant k is defined as the infimum of gamma of square root of f divided by f log f. Okay. So you see that also the log Sobolev constant is slightly better than the Poincaré constant. It's always true that one is smaller than the other, because if you replace square root of f by f, so you have, let's say, if f equal to g squared, what you get above is gamma of g, and below you get g squared log g. There are some some constants going around, but these are those constants that are just universal constants, so they don't really matter. And so you get that it's like computing the Poincaré constant, but with an extra log factor. So this one is so this means that the Poincaré constant is bounded by the log Sobolev constant. So if you can do log Sobolev, it's better. And so there is an inequality, which is that this is an inequality. V minus a log v minus log a is bigger than this thing. So this implies that k0 is bigger than 4k. So effectively, if you can do the modified log Sobolev constant, you can do the log Sobolev constant. And then you get anyway you get exponential decay of relative entropy in this case. Okay, and here there is a remark, is that I assume at the beginning that the chain was reversible. Okay, but it turns out that both bounds, the Poincaré and the log Sobolev bounds, are also okay for non-reversible chains. Meaning, if you define the log Sobolev constant like this, so this thing here makes sense for non-reversible chains, because everything makes sense for non-reversible chains, no? Because The Carré-Duchamp is a well-defined object for non-reversible chains as well. But the Carré-Duchamp is somehow symmetric, right? So in a sense, it only looks at the symmetric part of the generator. So you can check that the exponential bounds that you obtain using the Poincaré constant and the log-Sobolev constant, they also hold for non-reversible chains. So if you do the computation, there was one step there where I told you that you have to assume reversibility, but let's check it here. No, in the case of phi equals to 1 minus u squared, so forget about the 1. So what you get here is f times L star of f. But f times L star of f is equal to f times L of f, right? Because of symmetry. So you don't need to assume reversibility to get this identity in the case of the L2 norm. In the case of the entropy, you need to assume reversibility to get this identity for the modified log-Sobolev constant. But to get the bound with the log-Sobolev constant, you don't need to assume reversibility. Okay. Well, this is something you have to check. It's a classical computation. It's actually based on the fact that so let me see that it's based on the following fact. So it's based on this inequality. So entropy and L2 norm are special among relative entropy, and L2 norm are special among entropies because they can also use to measure the distance to equilibrium for non-reversible chains. Okay, in the sense that you have this that the derivative of the entropy is bounded by the Fisher information minus the Fisher information.
Milton, can I ask a question?
Yes.
Does this, I mean, you say the estimate works, but is the estimate that you get then, is that a good one? Because before you were making this point that in the non-reversible, it should work much more quickly than in the reversible.
Yeah,
And
exactly.
it looks a bit here like you're only keeping the symmetric part of the generator.
Exactly. So although they are true, they are not the good ones. Yeah.
Okay.
That's absolutely true. And if you want to do better, you have to be more clever. And in part, that's going to happen in that's going to happen tomorrow when I explain. Well, so tomorrow what I'm going to do is I'm going to explain the relative entropy method of Yau. Mm-hmm. So in relative entropy method of Yau, you still cannot take advantage of the asymmetry in a general way, but there is room, there is flexibility to make use of probabilistic arguments. So up to here, the entropy method is purely analytical. No? So we derive this bound. So you say, okay, the entropy, the derivative of the entropy is less or equal than minus the Fisher information. And now let's use a general bound like log-Sobolev, Poincaré, or something similar to get a bound on this entropy. What we're calling entropy, which is actually the L2 bound of the relative entropy in these two cases. But there is no probability. because you say, okay, this is function. We need to use this bound only for the density ft, but we don't know anything about the density ft because we don't really know much about probability. So we like analysis more. So we just forget about what ft is, and then let's prove something for every density f, and let's go fully analytic. So in the relative entropy method of Yao, there is room for probabilistic arguments. And on those probabilistic arguments is where you can actually take advantage of the asymmetry of, or the probabilistic aspect of the model. And in particular, you can try to make use of this asymmetry. Okay, so that's the that's the plan for tomorrow. So I think that's everything I wanted to say today. So I think we still have some minutes for questions if you have some.
Yeah, Milton, just to make sure I understood. So for the L2 distance, you are saying if I'm irreversible, the time derivative of the L2 distance is bound. It's bounded by the distance times the spectral gap of the symmetric part of the generator. Okay.
Yes.
And for the entropy, what is the analogous statement that it is bounded by? That you have to take the log Sobolev constant or related to the symmetric part of the generator again.
Exactly.
Okay.
Yeah. Okay. Exactly. It's exactly that.
Are there more questions in the audience?
So a non-technical question. So by the end of the mini course, you will explain how to apply, your improved version of Yao's method to this, for instance, to this reaction diffusion model. Is that the plan?
Hopefully, yes.
Okay.
Yeah, that's the plan.
Okay. Good.
And okay, so let me make just one comment. So for the moment, you see that here we are far from describing non-equilibrium stationary states because in order to compute the Poincare constant or the log Sobolev constant, you need to know the measure mu. So here we're running into a circular argument because, okay, I tell you, well, if you know the Poincare constant, then you know something about you will know something about the invariant measure, but actually you need the invariant measure to compute the Poincare constant. So we really need to do something else, or something different to really attack the problem of non-equilibrium stationary states.
Even to symmetrize the thing, you need to know the.
Exactly.
Yes.
Yes, exactly. Because because if you want to symmetrize the operator, you need to know the invariant measure.
Okay.
So we really need the other stuff if you want to. Because here you know the invariant measure and you can compute the Poincare constant, but if you don't know the invariant measure, you don't know the Poincare constant. Very good.
Okay.
So
thanks, Milton. Should we